Welcome. I'd like to welcome you to the first of the LPL evening lecture series for this fall. My name's Tim Swindle. I'm the director of the Lunar and Planetary Laboratory here. And before we get going, I wanted to make a few announcements. One of them is that if you are a student and you need to get something signed to get credit for being here, Josh up in the back, wave your hand, Josh. There's Josh. We'll stamp it for you. Then some other announcements, just some things coming up. I just kind of put the list over here, and I'll actually go a little bit farther than this. But there are a number of events coming up related to LPL, and so you might be interested in them. The first one is this Saturday at the Fox Theater. Binuval, an evening of space, art, and music, in part celebrating the asteroid Bennu, which is the target of the OSIRIS-REx sample return mission that will be launching less than a year from now. That's one of the two countdown clocks out in the atrium here, and you'll probably hear more about the other countdown clock during this evening's speech. But Binuval, it's at the Fox. If you're interested, they've got I don't have the URL for the website, but I think that if you do Binuval on Google, there's only one thing that will come up. So you can look there. Then other public events that we have, Wednesday, September 23rd, there is a series called Space Drafts at Borderlands Brewery. It's a series of public talks, and on the 23rd it will be Dr. Kat Vogt, who is a graduate of LPL and is now back here working as a postdoc and I think teaching a class. And she will be talking about her work on the dynamics of solar systems. Our next evening lecture in this series will be Tuesday, October 13th, basically a month from now. And that will be Dr. Veronica Bray, who is a member of the New Horizons team. So she will be talking about Pluto and the encounter with Pluto from the perspective of someone who was, in the control room there. That should be good. On the weekend after that, Friday, October 16th to Sunday, October 18th, we have what's called the Art of Planetary Science. This will be the third year that our graduate students have put that on. And the atrium out here, not just this floor, but the two floors above as well, will be filled with artwork of various kinds, photographs, drawings, paintings, representations of data, pictures from spacecraft. It's fascinating. It's been quite popular and probably worth your time to come see it. And then, moving on, there will be just a kind of different thing. We like engaging in different things. We have an art show one week, and a couple of weeks later, we're having a celebration of what's known as the U of A moon tree. There is a tree between this building and the planetarium. It's a sycamore tree that was grown from a seed that went to the moon and back. And that's been, 40 years since it's been planted. And it's a joint effort of the Poetry Center, the U of A Arboretum. The campus is officially an arboretum, if you did not know that, and LPL. And then we have a final lecture in this series in November. And let me see if I can pull that up. And I am not going to find it. Let's see. Oh, there we go. November. That's the one I wanted. So there's tonight's lecture, there's Dr. Bray, and then in November we have Dr. Christopher Hamilton, who does things like flying kites over volcanic lava flows in Hawaii and Iceland and all sorts of dull places like that. And he will be talking about his work in studying volcanoes on Earth and Mars. So we have a whole bunch of things going on, but of course the first one, and let's see, Josh, how do we switch this back to Bill's presentation? Or do you know what we're doing here? Anyway, tonight's talk is going to be by Professor Bill Hubbard. Professor Hubbard has been at the Lunar and Planetary Laboratory for more than 40 years. He was actually hired by Gerard Kuiper, the guy that this building is named after. He got his PhD from the University of California at Berkeley. Sort of in some ways things work full circle. He's now working on a mission where a lot of his collaborators are at Berkeley. They haven't been there the whole time. But he is one of a co-investigator for the Juno mission to Jupiter, and he will be telling us about looking at what's inside Jupiter just by flying around it for a while.
Thanks, Tim. Thank you. Okay, so Tim has already mentioned a couple of missions that are in the what are called the New Frontiers class of missions by that NASA flies. New Frontiers number 1 is the one that you just heard about this summer. It had an encounter with Pluto. That's also goes by the name of New Horizons, somewhat confusingly, and it's on its way now to its next target, and it'll take it a while to get there. New Frontiers number 2 is Juno, and so it will do its thing next summer. So this is going to be a little bit frustrating for me because I have no data to show you because we haven't gotten there yet, but I'll tell you what we're up to and what we expect to see. And I might mention that New Frontiers number 3 is next one in that class. These are all billion-dollar missions. Number 3 is OSIRIS-REx, which is, of course, headquartered right here at the U of A. So let me get started here and talk about why we're interested in going to Jupiter next. Of course, New Frontiers number 1 went to one of the smallest objects in the solar system, a planet that was demoted because it wasn't quite big enough, and so we're now going to the biggest planet in the solar system, a giant planet. And so why are we interested in a giant planet? Well, the thing that's happened over the last 20 years is that we now know that there are lots of giant planets in our galaxy. In this diagram here is a plot of planetary radius in Jupiter units versus planetary mass in Jupiter units. And those are the things that we can measure, not for every planet that we've detected in the galaxy, but for a certain subclass of them, and those are plotted here on this diagram. These aren't all of them, but these are the ones for which we have those numbers. And so Jupiter falls right here at 1 and 1, obviously, by definition. And then our other giant planet in our solar system is Saturn. And it turns out that Saturn is also going to be the subject of a Juno-like investigation in the next year. And so I'll mention Saturn peripherally, but this is primarily going to focus on Jupiter. Down here we have the Earth. So the Earth is almost is only at 3/1000ths of the mass of Jupiter. So much smaller, and its radius is about 1/10 of the radius of Jupiter. So it's way down here. So as you can see, there are lots of in our galaxies, just the ones that we've seen so far. There are quite a number of objects that are very, very big and very massive. And so the thing that Juno is going to do for us is it's going to give us a close-up look at a prototype, an archetype of this of giant planets, because for these other objects, for the most part, all we can measure is the mass and radius, but we can measure a lot more things if we can get into orbit around one of these objects. Why is this not shifting? There we go. Okay, so the thing about giant planets is that unlike rocky type objects like the terrestrial planets, like the Earth, they preserve a remnant, an important remnant of the material out of which the sun itself formed. When the solar system was only about 1 million years old, it still had an orbiting disk composed of gaseous material, hydrogen and helium, which were being incorporated into the sun. So this is a diagram, actually a numerical simulation of the formation of the sun here, and out here is a simulation of the formation of Jupiter. Now, we think that the way that this works is that in order to capture gaseous material, hydrogen and helium, into a planet, you have to have a nucleus, you have to have a gravitational well. So we have, at this point, we had basically two major gravitational wells in the solar system. One is the sun, still accreting mass, and the other is Jupiter. And we think that in order to get this process to work, you need to have a gravitational well of basically a giant terrestrial planet, or at least a giant condensed object of a mass of something like about 10 Earth masses. And we think that nucleus out of which Jupiter may have formed is presumably still there. So, but of course we can't see what the solar system looked like at an age of 1 million years, but we can see for other objects, namely, this is a young star which has an age of only about 1 million years, and this is an image that was formed by a sub-millimeter array in South America called the Atacama Large Millimeter Array. And this image was released this summer, and it shows a view of planets forming around this nascent star. These lanes here are presumably regions in which material is being pulled in by these gravitational wells, and so we're beginning to get confirmation from high-quality astrophysical data of this sort that this is how planets do form, in particular objects like Jupiter. So let's talk about some of the points that are of interest in connection with exoplanets. So we think many of these planetary systems that we see in our galaxy are dominated. We know, in fact, that they are dominated by one or more giant planets. The definition of a giant planet, as opposed to an ice giant like Uranus and Neptune, is that they are typically around 10 or more times larger than the Earth in radius. And as you saw from that diagram, some of them are considerably larger than that. And most of the mass in these planetary systems is in these giant planets, so they capture the so-called nebula, the hydrogen and helium part that was present when the stars were forming. So therefore, a giant planet will record the first 1 million years of history of the solar system. So it's a very important object to investigate in detail. And so what Juno is a special purpose mission that is designed to give us a close range view of this type of planet. Okay, so when I was interviewed by a reporter for the Star in connection with this talk, publicity for this talk, which was published over the weekend, I guess, one of the things he asked me is, okay, why are we going back to Jupiter? Haven't we been there a lot? And the answer is, yeah, we've been there a lot, but we haven't looked at Jupiter in the way that Juno is going to do. So here's a history of orbiters and flybys. So orbiters along the top, flybys along the bottom. So about the time I got to LPL, we had 2 flybys in rapid sequence. One was Pioneer 10 and then followed by Pioneer 11. I was a little bit involved in both of those missions. And so they did kind of like, they did the same type of investigation that New Horizons just did at Pluto. They went flying past Jupiter at very rapid speed, and so we got a brief glimpse of the Jupiter system before it was in our rearview mirror. Same thing happened in the 1980s when Voyagers 1 and 2 went by on their ways. Those were more capable spacecraft, but again, they did not linger at Jupiter. Then in the 1990s, we had a special purpose mission called Ulysses that was designed to investigate the heliosphere. So it wasn't really investigating Jupiter; it was just using Jupiter as a source of orbital energy to fling these spacecraft up into high heliocentric latitudes. So then Ulysses came back and revisited the Jovian system sometime later. Cassini, on its way to Saturn, also did a flyby. So again, very limited period of data. Galileo was a mission which was crippled by the loss of its main antenna link to the Earth, but it was able to get data back to the Earth in a very slow fashion, but it primarily concentrated on the Galilean satellites. And of course, New Horizons, the mission that just flew past Pluto, did in fact get a gravitational assist from Jupiter, but again, it was just a quick glimpse. So Juno is our first opportunity to have a lengthy investigation of Jupiter itself, getting in close to the planet, which is not an easy thing to achieve because the environment there is very hostile, as I will explain in a little bit. And of course, coming up, we have a mission to Europa, more than one mission to Europa, but those are different from investigating Jupiter. Okay, and I might mention one fictional mission to Jupiter, and just for fun, I'm going to contrast this science fiction mission to Jupiter, which was written by Arthur C. Clarke. This book was actually written about there, and it was for fictional, and I think a movie was made out of it, not this famous Kubrick movie, but a subsequent movie. But there were some limitations in the science there, and we can't really do a mission of that sort. But just for fun, I'll compare it to Juno. So here's what Juno is going to. Some of the main questions that Juno is going to address. One is, how did Jupiter form? Did it actually form in the fashion that the HL tau data suggest and the simulations suggest? And one of the ways we can test that is to see if the predicted massive core, the gravitational well that would be needed for that process, is still there. One of the things we can also investigate is, does Jupiter actually preserve what the sun's initial composition would have been from the same nebular material? And the Galileo entry probe, which was carried by Galileo, did in fact investigate a special region of Jupiter by entering the atmosphere, but some of the data are somewhat surprising, and Juno is going to take a more global look at that same question. Another thing that Juno is going to do, which I won't have time to touch on in this lecture, but we think we can investigate how deep the zonal winds on Jupiter go, whether they involve a significant amount of mass to affect the gravity field. And another question, which I can't really address at this lecture either, but is we will look at both the magnetic field and Jupiter's gravitational field and magnetic field at very close range, and that will give us clues about how Jupiter's magnetic field is generated. Jupiter has an extremely powerful magnetic field. Okay, so here is a diagram from a NASA app which I was just running when you came into the lecture hall, which enables you to visualize where missions are with respect to their targets. So this is a view looking down on the ecliptic plane with the sun up here and then the Earth over here. And so this is pretty much the configuration of the solar system as it is right now. And so Jupiter is moving along in its orbit, moving in this direction, and Juno is moving in its orbit in this direction, and they're going to join up next summer. And there is a countdown clock for Juno out in the lobby, which shows when that event will occur. So we're getting close now, and so we'll be seeing some data this time next year. This is a view from that app that I was running. So this is a visualization of Juno as it approaches Jupiter. So we're looking at Juno with the sun off to our right, and between the veins of this immense solar array we have here. Juno, by the way, is a solar-powered spacecraft. the first solar-powered spacecraft that has been flown to the outer solar system. And so its target, Juno, is visible between these veins. And if you saw that simulation, you saw that the spacecraft is slowly rotating at about 2 RPM with the solar panels facing the sun. Okay, so I'm going to, as I say, I'm just occasionally I will refer back to the 2010 Odyssey 2 book and movie, which was an imaginary Jupiter mission, which coincidentally is just about in the same time frame as we're talking about here. So the main thing that is different between fiction and fact is that we don't have a so-called Sakharov drive, which is pulse thermonuclear reaction. And so for dramatic purposes, if you're going to send a crewed mission to Jupiter, you don't want it to take as long as Juno takes. So you have to have some imaginary way of getting there fast. The other thing that that Clark visualized is that when you get to Jupiter, to get into orbit around Jupiter, you would use a technique which is a real technique called aerocapture. The way aerocapture takes orbital energy out is you scrape your spacecraft through the planet's atmosphere at just the right rate so that you take energy out of the spacecraft, and so when it pops back out of the atmosphere, it's moving slowly enough so that it's captured into orbit around Jupiter. That's the way it was visualized in this fictional account. Well, Jupiter, we could do that. Juno could do that in principle, and engineers have suggested that as a way to save on spacecraft mass, but it is way too scary to do it that way in reality. And so we're not going to do it that way. So here is the actual mission profile, which is much longer than the fictional account. Juno was launched in 2011, in the summer of 2011, 4 years ago. And so it initially, because it was launched with an Atlas rocket, it did not have enough energy to get it out to Jupiter. It would be impossible to load it we didn't have a rocket powerful enough to put it on a direct transfer to Jupiter, and that's the way most of these outer planets missions work. So instead, it was put in a lower energy orbit. Out here, its main engine was burned a little bit just to kind of trim its orbit up a little bit so that it would come back and execute a rendezvous with the Earth a couple of years later. About 2 years ago, it encountered the Earth. This is Earth flyby. And so what the Earth did was to add energy to Juno's orbit. When it flew by, it did a slingshot maneuver with the Earth, which then threw it into this new orbit, which now had enough energy to get it out to Jupiter. So it's now out about here, and it's just coasting along. So this is what is known as an inertial cruise. No burning going on. The only spacecraft around that sort of does burning as it moves along in orbit is Dawn, but that's a different thing from this fictional Sakharov drive. Okay, so anyway, JOI, Jupiter Orbit Insertion, is where you do a chemical burn to take the energy out. You don't skip into the Jovian atmosphere, you just do a chemical burn with the spacecraft's main engine. And that's going to occur currently scheduled, according to the countdown clock, it's scheduled for about 2 a.m. Universal Time on July 5th, which happens to be about 7 p.m. here in Tucson on July 4th. So that's pretty much going to coincide with the fireworks going off over A Mountain. Okay, so here's a description from Arthur C. Clarke about Leonov going into orbit around Jupiter. And I'll come back and talk about that. That's not totally irrelevant to the Juno mission, it turns out. Over here is a diagram of the real JOI for Juno. So this is a view here looking over the North Pole of Jupiter with the sun and the Earth off in this direction here. So Juno is going to appear to be coming into Jupiter in this direction. It's going to go right over the North Pole of Jupiter. And then over here, this inset here shows a view, the view from Earth now of where Juno is coming in over the North Pole of Jupiter. And so right about this point here it will start the burn of its main engine, and that's going to go for about 30 minutes. And then it will end over here, sort of symmetrically, so as it comes very close to Jupiter. So you could, in fact, do a Leonov type maneuver, but we don't dare do it that way. So instead, it's going to stay out of the Jovian atmosphere, and it's just going to burn its main engine. And so here's another view, again looking from the Earth of the diagram. So the white curve shown here is the initial orbit coming in, the JOI orbit, and these colored orbits are subsequent orbits as the mission evolves. So this would be scary, but this is plenty scary too. And why is it scary? Well, there are two reasons why it's scary. The first is that Jupiter does have a ring system. So this is where the ring system is known to exist. The data that we have from Galileo and other spacecraft indicate the Jovian ring system has this extent here, and of course on the other side as well. And so we think there's no material in here, but we're not totally sure. So we could hit something associated with ring particles, and that would be the end of our mission shortly after a mountain fireworks time. But the other main hazard for Juno, which is something that's going to be just continually there the whole time, and for any Jupiter orbiter, is the radiation belts of Jupiter. Now Jupiter has, just like the Earth, it has Van Allen belts, which are these high energy particles which are captured from the solar wind and then accelerated to very high energies in the Jovian magnetic field. And so you want to stay out of these radiation belts. Okay, so here's another view of the orbital setup for Juno. So now we're looking at Juno at the orbits from the Earth. So looking toward Jupiter. So Jupiter is over here, and these little red ellipses are the orbits of the Galilean satellites. So Juno comes in over here during JOI. It does its burn right in here. And then its initial orbit is going to be, this initial capture orbit is going to look like this. It's going to be very loose and go way outside of the Galilean ring system. And then it'll do a subsequent burn to kind of tighten up these orbits to get it in where you're not having to wait so long. But we'll have to wait a while for science after this initial orbit just because it's so loose. Here is another view of the evolution of the orbits, looking now down over the north pole of Jupiter with the sun up in this direction. And so Juno initially comes in like this, does its burn near periaps so that JOI occurs. Then this is its initial loose orbit, and then it'll do another burn, and it'll drop into these sequence of orbits. It'll do about 30, maybe more, maybe less, depending on what the final what the engineers decide to do. But so the orbits will evolve like this. So it will be a mission in which there will be moments of bursts of data that will come every 11 days or maybe 14 days, depending on how long the orbital period is going to settle down at. But during that interval, we'll be getting data. Now, I want to spend a little time talking about the radiation hazard, because this is something that a lot of people don't appreciate in connection with exploring Jupiter. It's a much more severe problem than it is even for Saturn. And so what is shown here are the radiation belts. And you have to appreciate the fact that these radiation belts are populated by electrons and protons that are accelerated to energies of 1 MeV typically, and some of the more energetic ones are at energies of 10 MeV. That's million electron volts. And the units that we're using for energy, electron volts, are kind of significant because an electron volt is the energy that binds together typically electrons in atoms and in molecules, whole molecules. The molecular binding energies are measured in electron volts. So if you've got a particle that's traveling with an energy of 1,000,000 electron volts, it can drill right through anything that is held together by molecular forces, and it will break apart those molecules and atoms. And it's what is called ionizing radiation. It's extremely ionizing radiation. So it can do a lot of damage. And these belts are populated with such a high density of these particles that it basically is a killing amount of radiation if it's sustained. So a short burst of it can be endured, but if it lasts, let me just put it this way: if in the fictional account, the Arthur C. Clarke account, if you were to actually spend, say, an hour in this environment, you would be dead. You would be very dead. And not only that, but it's interesting that electronics, many of you probably already know this, your electronic devices like your iPads and your iPhones and Androids and so on, that type of equipment, any type of electronic equipment like that needs to be in an environment that pretty much the same as a human needs. So what's fatal for humans is also fatal for electronics. The same, whether it's temperature or whether it's radiation, it's pretty much the same story. So a manned mission to Jupiter would have to put up with the same sort of concerns as an unmanned mission, and depending on what your acceptable lifetime is. Okay, so the way Juno deals with this problem is it has to have a very special type of orbit. Its orbit is designed to keep it from getting too deeply into the radiation belts for too long. So, but the way the orbits necessarily evolve means that you're eventually going to have to deal with the problem of too much exposure to radiation. So here's a diagram that's showing, again, looking at Jupiter from the Earth. And so initial orbit 1 is designed basically to keep out of these lobes of the Van Allen radiation belts of Jupiter. I might mention, by the way, that the Van Allen belts of Jupiter were measured for the first time by the same scientist who measured the Earth's radiation belts, namely Van Allen. He was an investigator on the Pioneers 10 and 11 missions, and he was a visitor to this laboratory more than once, and we enjoyed interacting with him. Anyway, the orbits of Juno will eventually, because of Jupiter's gravitational field, which it's not a perfectly spherical object, and so it's going to carry the orbit into this type of evolution. So eventually, by orbit 31 or so, we're going to be dealing with a very exposed spacecraft, and so it's going to go downhill as it moves along in its mission. Okay, I might also mention that for the same reason, the reason we have to have this type of orbit means that here's Io's orbit shown to scale here. So we're not going to be able to get very close to the Galilean satellite. So it's not going to be a Galilean satellite mission. So it's not going to get close to Io or Europa. And so the Europa mission, which is planned for subsequent years, is kind of a very different type of mission from Juno. Okay, so let me talk about how Juno deals with this radiation issue. So how do you protect against radiation? Well, there is a vault that it's carrying. And these are a couple of pictures that were made of the vault when the spacecraft was being assembled. Here you can see the main body of the spacecraft and a human here for scale. This is in the special clean bay at Lockheed Martin up near Denver, which is where where Juno was assembled, and I think it's also where OSIRIS-REx was being put together at some point. So this radiation vault is made out of titanium, rather thick titanium. And so the more sensitive instruments are encased in this radiation vault, which is then shown up here, mounted on the spacecraft. So let me quickly talk a little bit about this spacecraft, which is a unique spacecraft because of the solar power. So the Galileo spacecraft was nuclear powered. Cassini is nuclear powered. And NASA, in order to keep the costs down, in order to keep the environmental reviews down, decided that we needed to have a spacecraft that would not have environmental issues. So when it was launched, you wouldn't have to worry about the possibility of a nuclear power plant being exploded and distributed over Florida and the Atlantic Ocean. So this spacecraft has huge solar panels. And so here to scale is a human. And so you see these three big solar panels. They deployed very nicely after the spacecraft was launched, right after it was launched. And they unfolded, and they're now working quite well. And they will deliver a modest power at Jupiter. And not as much power as you would expect, just because Jupiter is so far from the sun. And but it's quite stable. The spacecraft spins about this axis, so it has a very large moment of inertia, and it's ideal for measuring gravity. That's the kind of spacecraft you want when you're going to make very sensitive gravity measurements. I'll talk a little bit more about the gravity science, but basically there's the main antenna, the main dish, which links the spacecraft to the Earth, is located right here on this axis. And then there are a number of experiments that are distributed about the spacecraft. We have a magnetometer that's going to make very accurate measurements of Jupiter's magnetic field. And on the other side of the spacecraft, this is the sun-facing side of the spacecraft. On the other side of the spacecraft, we have the main engine here, which is going to fire to get it into Jupiter orbit. We have some detectors here. Won't have time to talk very much about them, but I will mention that there is a special camera on board called Juno Cam. Now, Juno Cam hasn't taken any spectacular pictures yet, but it will. When it comes in, when the spacecraft comes in over the north pole of Jupiter, goes very close to the equator. It'll go within a few thousand kilometers of the cloud tops, passing over the equator of Jupiter, over the equatorial regions of Jupiter, and then it will come back out over the south pole of Jupiter. So it will be taking some very spectacular images of Jupiter, quite unlike anything you will have seen of Jupiter. So that's something to look forward to for next summer. Another experiment which is relevant to the interior of Jupiter is the microwave radiometer, MWR, which has 6 antennas that are arrayed around the body of the spacecraft, and which I'm going to talk about in a little bit. I'll say a few more words about that. Some of these other experiments are dealing with the aurorae and the energetic particle environment at Jupiter. Okay, so let me say something about the gravity science experiment, which is what I'm mainly associated with. So the high gain antenna is here, and that dish will be pointed toward the Earth when Juno is doing its gravity measurements. And so that will transmit a very highly calibrated beam of microwave radiation at about 2 centimeters wavelength. And those so-called Ka band, and those will be received by the Deep Space Network. The Deep Space Network is arrayed around the Earth so that you can always make measurements of the spacecraft regardless of the time of day. But this is an example of one of the antennas that's used on the Earth to receive these signals. So this is capable of measuring extremely small changes in velocity of the spacecraft, which is what we use to measure the gravity of Jupiter. The other experiment which is relevant to the deeper parts of Jupiter is the microwave radiometer, which has these antennae which are designed to measure microwaves at a variety of wavelengths. So here's some of the other antennas, which are on the other side of the spacecraft. And these will probe into Jupiter's deep atmosphere. And the largest antenna shown here will be able to measure down into the Jovian atmosphere at pressures exceeding 100 bars. So it will be able to corroborate or not corroborate some of the measurements that were made by the Galileo entry probe. So one of the questions with Jupiter's water, which we can also indirectly address with the gravity measurements, is does Jupiter's water content match what we think ought to be there based on what the sun has in terms of oxygen content? This is an artist's conception of basically an HL tau type visual. It looks pretty much like HL tau, actually. I think it was done before HL tau was detected in that fashion. Okay, so what we do basically is so using gravity and microwaves, we can look into Jupiter's atmosphere. The gravity is going to tell us about the distribution of mass in this part of the planet, and because Jupiter is not spherically symmetric, because it's distorted by rotation and tides, we can actually probe into this part of the planet. And then in the outer part of the planet, using microwaves, we'll be looking into this part of the planet. So the gravity experiment is actually a very elegant one, which is designed to measure Jupiter's gravitational shape to about 1 part in a billion, using this highly sensitive Ka band experiment. We'll be basically measuring the distortion of the wavefronts of these Ka band waves as they arrive at the Earth. And using this analysis, we can basically apply a theory which was first derived back in about 400 years ago, starting with the mathematician Maclaurin. What is the shape of a rotating planet? It turns out it has a lot of components to its shape, some of which are detectable from Earth and or using a limited number of flybys, and some which require an orbiter. So right now we've measured these components of Jupiter's gravity. This one not to sufficient accuracy, and then these components will be accessible to Juno. Similarly, we will be able to measure how Jupiter deforms as it's orbited by its satellites, primarily Io. And so those are shape components that will also deform the shape of Jupiter. And these will be detectable by Juno at the level of about 1 part in 10 to the 7. Okay, so I'm going to wrap this lecture up by saying a few things about Juno's special passengers. And this is sort of a public interest type of aspect to the mission. Our principal investigator, Scott Bolton, I think his sons are no longer at the right age, but at the time the mission was being designed, they were very much into Legos. And so Scott arranged a deal with the Lego company to include some things on the spacecraft. We also have a tribute to our Italian partners and to their distinguished compatriot Galileo, who of course was one of the first. He was in fact the first scientist to really apply modern science to the planet Jupiter. And so the spacecraft has this little plaque on it, which is a reproduction of Galileo's notes of his first observations of the Galilean satellites. So that's on the spacecraft. But the other thing that's on the spacecraft are these Lego figurines, which there are 3 of them, and they're made out of special aluminum alloy, and they're specially bonded to the spacecraft deck here. And you know how big Lego figures are, so these are standard size figures. So the one on the left is Jupiter, of course, the god Jupiter, with his lightning bolts. And then this is Juno with her magnifying glass. In mythology, Juno was the one who was constantly investigating Jupiter to see whether he was being faithful or not. He was not most of the time. And so that's where the name of the spacecraft comes from. And this is Galileo. This is the Lego version of Galileo with a Jupiter globe and a telescope. So are these available in stores? I don't know. We'll see. It would be nice. We're hoping that Lego will issue a Juno model with these figurines. Okay, so the end of the mission is going to come in the following fashion, and this is still being sort of discussed, but this is what we think is going to happen to the spacecraft. So here's some artist conceptions of the final orbit of Juno. And the final orbit of Juno is going to be like the JOI that was described by Arthur C. Clarke. Only this time it's not going to emerge from the Jovian atmosphere. It will simply leave this incandescent trail of Juno parts, Juno molecules, and hydrogen as it enters Jupiter's atmosphere and burns up there. So the reason for this is that after 33 orbits in 15 months, that's the nominal mission. It may go a little longer than that, but it's going to have been really dosed by radiation, even with these specially planned orbits. And so because of that, because it's going to make Juno uncontrollable if we let it go on too long, NASA insists that we, before it becomes uncontrollable, that we get rid of it. And the reason is that we don't want any risk that it will contaminate Europa, because Europa is thought to be a possible site for extraterrestrial life, and we don't want to put any terrestrial life on Europa by accident. So planetary quarantine demands that we do it in this fashion. Okay, so if you're interested in Juno, I can give you some places to go online. There is if you go to the NASA website and under mission pages, you will find a Juno link that you can click on, and it will give you information about Juno. There is also a Juno website which is independently designed. It's produced by Juno. It's run out of Southwest Research Institute, and so you can go to this site, and this one has some movies with some of the investigators talking about what interests them in Juno and Jupiter. And then there's a nice app. If you haven't downloaded this free app, you might want to do so. It's a visualization. It was the one I was playing for you when you walked into the room, and you can. It's NASA Eyes is what it's called, and it will download to your computer, and then you can run various buttons and see where various missions are and what they're doing, and it's a nice simulation. So I think with that, I will conclude my talk, and thank you very much for your attention.
Thank you. We've got time for a few questions. Let's see, Josh, do we have another microphone to? Yeah, so there's another microphone that if you'd raise your hand, Josh can come and get you questions. Down here.
Yeah, Let me just mention that this is being recorded. This lecture, and so in order to get the questions on the recording, we need to have you mic'd.
So do you think the spacecraft will be able to detect the layer of water if there is one on Jupiter, or are there any theories about there being a layer of water somewhere in the depths of Jupiter nowadays?
Yes. What happened with the Galileo entry probe was that it was sent into a region near the equator of Jupiter, which turned out to be one of the hot spots, which had very few clouds, and it was thought to be depleted in retrospect, depleted in water because it was basically a special zone, and so the entry probe, it failed. It got too hot at about pressure about 22 bars, and at that point it was still seeing the water abundance rise, but the water abundance was not what it was expected to be. It was way low. It was a dry spot. And so the microwave radiometer will be able to probe much deeper than that and in a more global sense. So we will get an idea of whether the Galileo probe results were really representative of the whole planet or whether we've got a different water abundance than it detected.
Questions? Questions about Lego? Yeah.
You mentioned some parallels between what Juno will be able to do and what Cassini will be able to do when it finally crashes into Saturn. Could you speak to what those parallels are?
Yeah. It's Cassini is in an extended mission now, and its final act will be to drop it into a Juno-like orbit where it comes very close to Saturn. It will actually orbit inside of the ring system. So that alone is cause for concern. It may not make it out of that first orbit of that type. But assuming it does, it will be able to send similar data back to the Earth of the type that Juno will be getting from the gravitational point of view. So it will be measuring some of the same gravitational components for Saturn that Juno is measuring or will be measuring for Jupiter. It wasn't planned that way. It wasn't planned that we were going to have this duo of geophysical gravity orbiters around our two giant planets, but it's working out that way. So unless something bad happens, we'll be getting very nice data. Now, I should mention that Cassini is not equipped in the same way as Juno. It doesn't have a microwave radiometer experiment on board, and nor does it have a working Ka band, which is what you require for really high quality gravity data. However, the Cassini mission, the geometry of the Cassini mission is slightly more favorable for that type of measurement than Juno is, because Juno is set up so that you're looking at it kind of always visible from the Earth. And anyway, for technical reasons, some of these things cancel out. So we expect to get data from Cassini, which will be rather similar in quality to the data that Juno will get.
You said you wanted to compare the water in Jupiter with water in the sun?
Well, of course,
the
water molecule doesn't really exist in the sun. It's way too hot.
That's what I thought.
So it's just there as oxygen, atomic oxygen. So the oxygen abundance is the key thing, and water, of course, is a very important molecule. It's very important to know what its initial inventory was in the solar system. And so if we get an accurate measurement of the water abundance in Jupiter, that can be compared with the oxygen abundance in the sun.
Any more questions?
Is there any capability to spectroscopically search for any other chemical species besides water, or is that your primary goal?
The molecules that we expect to be rather abundant in in Jupiter's outer layers are the three hydrides, H2O, water, ammonia, NH3, and methane, CH4. And so those three molecules, in particular ammonia, are detectable with the microwave radiometer experiment. So there will be some information about all three of those.
And let's thank Professor Hubbard again.